In this next example on entropy, we'll be able to get a better understanding by showing how this works over here. So here we actually have a heat exchange. We have a hot cup of water, 250 grams. It's about a quarter of a quart. And we have a cold cup of water, same amount, 250 grams. The hot cup is 100 degrees centigrade. The cold cup is at 0 degrees centigrade. And there is a heat conductor that connects the two cups so that heat can travel from the hot cup to the cold cup, and those little Q's that represent heat traveling from one to the other. And eventually, they both will be at the same temperature. This one will cool down, this one will heat up. And since they had the same amount of water in them, they will actually both end up at 50 degrees centigrade, providing no heat is lost to the environment, so make it simplistic. And in this heat exchange, we're going to have a change in the entropy, and of course, as we expect that to be a positive change. Entropy always goes up when there's an exchange of heat. So how do we calculate the amount of the entropy change? Well, since the temperature is changing, we probably want to use the integral of that, in the formula that uses the integral, but I think we can find a simplistic way of doing it. So if we say that the change in the entropy is equal to the amount of heat being exchanged divided by the temperature at which this happens, and notice, let's take cup number 1 first, that starts at 100 degrees centigrade and it ends at 50 degrees centigrade. So it's a relatively small change in the temperature, and if we take the average temperature during that exchange, we come up with a pretty close value, a pretty accurate value using that equation right on the integral. So let's go ahead and do that. So we're going to use the average temperature. Now that is a good approximation that usually gives you a very good answer. All right, now how much heat was exchanged? Well, the water changed from 100 degrees centigrade to 50 degrees centigrade, so the delta Q is going to be equal to mc delta T. Now, is that going to be positive or negative? Well, since we're taking heat away from the cup, that has to be a negative quantity, so it needs to be a minus mc delta T, divided by the T average at which this occurs, T average. Now, another way in which you can do this is not worry about the negative sign and simply say that the final temperature is smaller, the initial temperature is greater, and if you then, of course, subtract delta T can be written as T final minus T initial, that means you'll get automatically the negative sign. So we can think about that and say, okay, we don't need to worry about that if we just strictly stay with the proper delta T. In other words, we're going to write this as mc times T final minus T initial divided by T average. And then that will automatically give us the negative of the heat exchange. All right, let's plug in the numbers that we have. So this is equal to, the mass would be 250 grams times C. Now for water, C is 1 calorie per gram per Kelvin. Centigrade degrees or Kelvin, same thing. And times T final minus T initial, so that would be final would be 50 degrees centigrade minus 100 degrees centigrade. Now we don't have to convert that to Kelvin per se, because Kelvin degrees and centigrade degrees are about the same size. Now we do have calories in there, and we want to convert that to joules, so we need a conversion factor of 4.186 joules per calorie. So now we can see that calories disappear, grams disappear, so we don't have to worry about that. And then we have centigrade degrees and Kelvin degrees, so that cancels as well. We still have to divide that by the average temperature. Now the average temperature would be, let's see here, in this case, T average would be equal to 75 degrees centigrade, which converted to Kelvin, we have to add that to 273. So let's make sure we get that right. 273 plus 75, that would be 348 Kelvin. All right, so we divide that by 348 Kelvin, and now you can see the units are going to be joules per Kelvin, and that's correct. So 250 times a negative 50 times 4.186 and divided by 348 equals, and that would be a minus 150.4 joules per Kelvin. Now notice it's a minus. And you say, well, wait a minute, didn't you just tell me that the change in entropy is always positive? How do we get a minus out of that? Well, that's only for this part of the process. We still have to find the change in entropy for this part of the process. So now this was 4.1. now we have to do the same for delta S for part 2. That's the cup that receives the heat, and since it's receiving heat, that delta S will be positive. And since it happens at a lower average temperature, that will be a greater quantity, and you can see that a greater positive quantity will negate the smaller negative quantity. You'll see in just a moment. All right, so again, we have 250 grams of water in the cold cup, 1 calorie per gram per Kelvin. The difference now would be final temperature, which is 50 degrees centigrade, minus initial temperature, which is 0 degrees centigrade, times a conversion factor, 4.186 joules per Kelvin, and then the whole thing divided by the average temperature for the cold cup. Now that would be from 0 to 50, so T average in this case is 25 degrees centigrade. That means T average in that case is 298 Kelvin. All right, so that goes down here, 298 Kelvin. So let's figure out what that is equal to. We got 250 times 50, that's a positive 50, times 4.186, and divided by 298. And here we get delta S2, and let me write here delta S1, so we compare it, is 175.6 joules per Kelvin. Now, for the total change in the entropy, delta S, that is equal to delta S1 plus delta S2. So what you can see here is that you have to add the entropy change of every piece of that heat exchange. In this case, there's two cups of water, so we have to add the entropy change for both cups of water. So for the first cup, it was a negative change because heat was removed, 150.4 joules per Kelvin, plus the heat exchange here is positive, so we have 175.6 joules per Kelvin, and that means we have 150.4 negative plus 175.6 positive, so we have a 25.2 joules per Kelvin, which is the delta S for this heat exchange. For the amount of heat that was exchanged from the hot cup to the cold cup, the universe's entropy increased by 25.2 joules per Kelvin, which means that's how much less available energy is to do work after you exchange that heat. And that's how you do that problem.